I want to talk about how you can tell the difference between a thunderstorm local energetic increase in, let's say, the Schumann resonances, and just in general the electromagnetic spectrum, like a big release, or rather a big increase in photonic density, which you can feel, perhaps, bioelectrically, depending on your sensitivity, versus a space weather, global increase in photonic density like we see here. So we have this really great opportunity as measured by the Space Observing System out of Tomsk, Russia. Yes, they just recently had some really crazy data. According to them, it was an issue with their substation. So I'm sure a lot of you that will watch this video or are watching it right now are came in and joined my channel as a result of all that craziness that happened then. That's what they said it was. They said it was a substation power issue. It looked like PAM4 signaling, which is something that was new to me, probably new to a lot of us. I'm just going to pop out the live chat really quick. Yeah, okay, we got at least one person, great. And I want to take this opportunity to talk about these changes in photonic density in the environment, whether they are local or whether they are global, because a lot of people will look at this and they'll correlate it with, let's say, some health and wellness symptom. Fatigue is very common. It's a very common one. Maybe like headaches, things of that nature, versus a global event, which actually does have the potential to perhaps cause a bioelectric dysfunction. Now, a local event like a thunderstorm can certainly do that. And let's go back to our main graph here. A thunderstorm event can definitely do that, but it would be for your local area. So in this video, I'm going to show you the difference in how you can tell between the two. So actually, that's not the right one. We want the other one. I think we want, oh, nope, not that one. We want this one. Okay, so we'll get into the global effect and how we can tell it's global, but I want to start with this local increase in photonic density in the Schumann resonances as measured by the Space Observing System. And the first thing is you have to, think about how a thunderstorm progresses, is that it starts off typically building and growing, and then eventually reaches full expression. It has intercloud lightning strikes. These big electromagnetic potentials develop. You have huge positive potentials, huge negative potentials. You have these arcs of electric energy between them. Free electrons are flowing around. Sometimes they discharge to the ground. But what happens is typically a thunderstorm will move. It will travel. And sometimes they can travel for a very long time. We all know hurricanes, right? They can travel and feed and sustain themselves for days and days and days. But they will travel typically over an area at some speed. And so what we can see here with this increase in the Schumann resonances, this 0 to 40 hertz band, right there, 0 to 40 hertz. This is our time axis down here, UTC plus 7 time, is we see that it starts off just in the lower frequencies. It has this shape to it, right? This kind of like upside down teardrop shape. So we see that it really shows up nicely in the lower frequencies to start, and then it expresses itself across the 0 to 40 plus hertz, right? We see it even going beyond 40 hertz there. Before it then subsides, and actually here it goes back up again. It has like a double peak before then subsiding to mostly just the lower frequencies that are receiving this higher power density. Like right here, we have high power at this point in time. So let's say it's about 1930. But then right there, it's only a light green. It's like a medium power density. So why is this light green, whereas this is white? This is high power, this is low power. It's because of the frequency, folks. If you have a higher frequency, it's pulsing more times per second. It has a faster cycle rate. And as a result, it has more chances to interact with matter. As a result, it has a higher attenuation. So the air overall is pretty non-reactive with electromagnetic waves. That's why we can have the Schumann resonances here propagating nicely and continuously in Earth's atmosphere in between the ionosphere and the surface. They also do exist in the ionosphere, and they've been measured bleeding out into space, and they propagate in the lithosphere. So it's a little bit more complex than just an atmospheric phenomenon, but the lower frequencies will attenuate less because they interact with the air less often. They're closer to the air is fairly close to a vacuum, you could say. I mean, it's not 100%, but it's much more vacuum than, let's say, solid rock. And so these lower frequencies, they do not interact as often. They attenuate less. The signal can carry on to a greater degree. And that's why you can have high power show up in these lower frequencies, whereas the higher frequencies reduce in strength, because now the thunderstorm is further away. As the thunderstorm in your local area, let's say, for here it was Tomsk, Russia, and we actually have the weather data. So let's just show you that right now. See right here, 1800, there is your thunderstorm. So there was some lightning activity. Of course, we see here, this is the 28th, and it's the 1800 mark right there, okay? So we have this thunderstorm activity. It was passing over the observation station that was collecting this electromagnetic data. As it got closer, then the power densities increased, the photonic density increased. It looks like it had two main components to this thunderstorm. There was two maybe cells that were the strongest, and then it finally passed over and reduced in strength until it just kind of went back to normal. We even see these lines here kind of fading out. Now here is where we have the space weather activity. But what's important to keep in mind, why I'm making this video, even though it's pretty late at night here in Riga, is because a lot of people will look at this and say, oh yeah, I was having all these crazy health effects, but this is a local thing. So it's good to take personal observations. If you're feeling unwell, or maybe it's on the positive side, you have a lot of energy, a lot of creative juices flowing, whatever, right? Whatever it is, it's good to take personal observations, whether it's in a journal, whether you just have a really good mental system. I would still recommend you write it down if you're looking to have develop a feeling for these energetic movements and changes, because they certainly exist. To say the earth is dull and lifeless is a lie. The earth is alive and teeming with life and energy, and this energy is across the entire electromagnetic spectrum. I mean, you can say this for any location in space-time, but we live here on the Earth. So these Earth energies are always changing. The Schumann resonances are fairly stable, as we see them here, right? I mean, they do increase and decrease slightly in frequency and slightly in power over time, and we evolved in these. So that's why when they have these big changes like we see here, it can be dramatic, because all of a sudden what our body's used to at a very low level is now experiencing a 10, 20, 100x in energy density. For example, this is our frequencies. If we go here, this is our relative amplitude, and we see mode 1 there went to an amplitude high of 82. This one maybe is about 77 or so. Mode 2 at 14 hertz went to an amplitude high of 62 twice. It had a double peak, perfect double peak according to this data. And then 51 for mode 3 at 20 hertz, 41 for mode 4. But you can see where they normally are. The power density is normally there, and then this thunderstorm rolled over and dramatically increased it. But the thing is that unless you're living in Tomsk, Russia, you're not going to feel that. Yes, you'll see it on the screen because they have this public data feed, but in regards to the bioelectrical interaction with you, if you're 500 kilometers away, 5,000 kilometers away, you're not feeling this bioelectrically. It's blending into all the other electromagnetic inputs into the Schumann resonances. I mean, there's like 100 plus thunderstorms going off at any moment. I think it's more than that, but it's 100 lightning strikes a second. So it's not at all abnormal for there to be thunderstorm activity at any point on the globe at any given moment. So this is just a normal thunderstorm if you're not living there, and it's not affecting you, except in it's like the voice of a million people culminating into one larger energetic push, let's say, right? It's just one voice of a million. But if you are living in that area, then you would have felt this. Now, the reason I'm talking about this so much is because everyone experiences thunderstorms every now and then. And if you are in an area that has a frequent thunderstorm activity, then you're going to be experiencing things like this often. And the way to know is there a thunderstorm overhead? You might not have a local data feed for the Schumann resonances, but this is a pretty typical signature. So you can write down the length of the thunderstorm, when it started, how far away it was. Like, you could play scientist if you want, and then you could write down all the things that you felt, whether you felt good, whether you had health and wellness symptoms like fatigue or headache or brain fog or whatever, and you could do that. Now, here though, this is where it gets interesting. Here we have a global electromagnetic pulse of energy, and the reason why is because we have quite a bit of evidence to suggest that it is a global one. So this is something just today, this was yesterday, this is something that you may have felt today, and that is why it's also good to journal and write down these things, because then you could potentially correlate this with the exact times that we see here. We have 1800 to 1400 UTC plus 7. This is Tom's local time here, so that right there would be 1300 UTC to 9 a.m. UTC. If you're in America, that is Eastern Daylight Savings Time is -4 UTC, and Pacific is -7. So if you're on the West Coast of the United States, this is actually a complete flip-flop. It's a 12-hour difference. So you can look at 6 o'clock p.m. and think 6 o'clock a.m. And if you're on the East Coast, you add 3 hours, or you -9, depending on your math there. You -3, or you add 3 onto the Pacific, or you -9 off the actual. But if we look here, we have 1800 to 1400, and now we're going to go into our browser here. We have it right there. We can go to another source for the Schumann resonances. We have VLF.IT. This is this VLF Open Lab, and they have a whole bunch of Schumann resonances and very low frequency electromagnetic wave monitoring stations. They have a bunch in Italy, and they also have a good one there in Canada. They have one in France. I like the Cumiana and the one in Canada. Cumiana has a little bit of electromagnetic pollution near it, but still every now and then it's a good source. In general, it's a good source. The Canada one seems to be better. So you can see the location of it there, and for Cumiana, you can see the location of it there. Now, when you look at these data feeds, you want to make sure what's happening in the area at the time. So if we go down to the bottom, looks like there's some thunderstorm activity near Cumiana, Italy. So things can get complex. You kind of have to know your stuff to really put this together. But that's why I'm making this video, to help you out so you can learn this stuff and do it yourself when it's happening, when needed, because I can't make videos for everything. So what's interesting though is we look at the data for Cumiana, Italy. Here is today, and we have our most recent, if I increase, oh, it does go, nice. If we look here, we see activity. This is 1200 UTC, this is 1800 UTC, and this is 600 or 6 a.m. in the morning. So we have a 7-hour difference between times. So the time of that global burst here, right, 1800 to 1400 is, if we do the math, 9 to 13. So we look here, here's 6, here's 12. That would make 9 right about there. And we see pretty quickly after 9, at least in Cumiana, Italy, we start to see these increases there in the 0 to 50 hertz electromagnetic spectrum. This big wave at exactly that time, I mean from 9 to 1 was when it showed up in Tom's. Here we're seeing it more from, let's say, like 10 to 2:30 or so. And here's the most recent data. And this right here would also be lightning activity too, most likely, because again, remember, we do have these lightning storms right near Kumiana. So this big increase is probably due to some local thunderstorm activity, but the global signature is paired on top of it as well. And then this is likely all thunderstorm activity. Now the reason why I say this is likely the global, and probably a little bit of a blend of some of that thunderstorm, is because we can also look at the Canadian data. So here we have the magnetic field from 0 to 50 hertz, from 1800 UTC all the way to 1200, and we also have longer strips there. But we can see here, right at 1300, which is the end time for the Tomsk global burst, is we see a very nice increase in the photonic density as measured by the magnetic field, going from 0 to 50 hertz. So we have three sources right here. This is not by any means like 100% conclusive, but we have one, then we have two, and if we go to our bigger one here, then we have three sources for photonic energy density increases as measured by the Schumann resonances electromagnetic frequency band across different parts of the globe: Canada, Italy, and Tomsk, Russia, which is near Mongolia. So pretty different far-flung locations, all northern hemisphere. Let's keep that in mind. But more evidence to suggest that there is some sort of global energetic density, photonic density increase that occurred by looking at the electron flux data for the radiation belts. Now this is collected by the GOES geostationary satellites at the, they're located in the radiation belts at 5.6 Earth radii. So they are, they're spinning with the Earth. So they're moving through the radiation belts in different ways, and there's two of them. But we can see here this big drop in the electron flux. And what are the times in UTC? Well, we have this one here. There's two of them slightly separated. So we have this one here at 4:30 a.m. But then we have a simultaneous one there for both of them, which is a little odd, right? This red one didn't go down. We had a simultaneous drop for both of them. Look at that, 9:30, 10, right, all the way until about 12 or so. So big drop in the electron flux. Now, what does that mean? That means that the radiation belts that surround the Earth, and I can actually, I think, pull up the radiation belt data. So so you can see what that looks like. I just need to go to my bookmarks. That should do it right there. Okay, we can actually look at our model here showing this drop in the radiation belt electron flux density and how these electrons got dumped. Now, where do they go? Well, they went to the ionosphere. When the radiation belts get pressed on, they can shoot and move their ions and electrons and protons towards the Earth. So let's zoom back here. Let's actually go full screen, and we want, this is the 28th. Oh, they might not have updated it yet. This might still be. Oh no, here we go. Right here. Okay, we have 10:10, and so we just go back just a little bit. Let's look. It goes pretty quick, but look, what you want to look for is it going from red to like yellow and blue. Okay, so we want these lighter colors like this instead of these heavier colors. And we see that right there. It's very quick. I mean, this just happened, folks. But we see there now it's quite a bit different than here. Right there, it's more red. Then we see this lightening of color and also a condensing, especially there, a condensing of the radiation belt. So what happened was there was some sort of space weather event, whether this was a change in solar wind temperature, speed, density that pressed on the radiation belts. These electrons then spiraled in towards the Earth and interacted with the ionosphere. If you look at the global ionospheric data as we have here, I think I can zoom in there too, make this a little easier for you all to see. We can do the past 2 days, and this will start on the 28th, and we're going to see the change in the ionosphere, as compared to yesterday, a big drop in the frequency because there are more electrons precipitating down into the ionosphere, changing the electromagnetic potentials. So here we're on the 28th still. I can change this to 2 hours per second. And let's look for the 29th at around 10 to 1400, right? So here we are. Everything's pretty normal. No big changes from yesterday. Then we see this big... Where are we going? One second. This is looking just a little different when I played it just a little bit ago. Let me scroll to the end there. And let's just zoom in on our time specifically. Yeah, okay. So here we have like our normal ionosphere, like this. And then if we scroll forward to about the time that the electrons are precipitating out of the ionosphere, we see these big increases in the megahertz. So the overall frequency, the dominant frequencies of the F2 layer, the outermost layer of the ionosphere, increased. There was a change as compared to yesterday in these frequencies in these parts of the globe, which is, as you can see, the northern hemisphere. So we can see how, especially like right there, see it really nicely. Now this is later in the day, but you can see these changes in the ionosphere correlating with the electron precipitation. So you have some sort of space weather event, and then you have electron precipitation from the radiation belts into the ionosphere. The ionosphere potentials change, and that creates a little bit of a local Schumann resonance outburst, and you perhaps felt that. So I wanted to explain and show the differences between a local effect and a global effect, and how you need to be very mindful of which one is which. So this is kind of a characteristic pattern there. If you see that, that doesn't necessarily mean it's local, like from a thunderstorm, but it's very good to type in past weather, Tomsk, Russia on Google, pull it up, time and date. They have a good website. See if it happens, see if it correlates. There, it's a perfect correlation. See, 1800, and there, 1800. So, I mean, they record this in 6-hour blocks right there. So it's important to look at other sources like we have here out of Cumiana, Italy, and out of Canada, and to then also look at space weather data too. So wanted to go into that, and I hope you found that useful. Check out some of my other videos. I'll put the stuff in the video description. Thank you all so much. Much love, peace, love, blessings. Namaste, and I'll see you all in the next video.